plate that I now know to bring your plate. So make sure you bring your
Flatware. Flatware. Yeah. All right. Well, as Ellie introduced, I'm Caton Mande. I'm an engineer over at the Cooling Center. I see that we're very Cooling Center heavy again today. On the agenda, I was supposed to talk about our work developing a advanced automatic termination controller for clothes dryers. However, I haven't had a chance to actually compile all that information into a coherent presentation, so I'm calling a little bit of an audible, and I'm going to talk to you today about our tracer gas airflow measurement system, which is quite interesting, I think. So that didn't, oh, it's not plugged into my computer. Also do this. Okay, so the tracer gas airflow measurement system is a device that we have developed in-house that allow us to take high accuracy airflow measurements in laboratory and field settings. The reason that this is important is for a lot of our work, measuring how air moves is very important. Whether it is through a fan, how much ventilation is actually being entered or brought into a room, leakage through a ducting system. So even if you know the air that's coming through your fan, that doesn't mean that it's actually getting into the room. And then another one, which it can be used for, and we haven't really done a whole lot of work with it, but is room air quality stuff in terms of air change rates. So I'm going to briefly give you an example of why this high accuracy measurement is so important. And I'm going to do that by talking about sensible capacity. So sensible capacity is a metric that we use when you're talking about an air conditioner or a heating system. And it's the amount that the temperature of the air changes as it passes through that system. So you can see it's a linear equation. It deals with the mass flow rate of air, the heat capacity of the air, and the temperature entering and exiting the system. This isn't the total amount of capacity that the system will provide. This is just looking at the temperature difference in the air. So as you can see, there's going to be two main sources of air that come into this with your measurement. You have your temperatures and your mass flow rate of air. So at a typical room air condition, your temperature sensors are pretty accurate. You're talking about 0.4% of your reading, which is pretty small and pretty good. Now, if you look at the available airflow tools that are on the market, you now have a range that's 2.5 to 10% of your reading, which is significantly bigger than 0.4%. So what does this actually look like? So on this chart, on the x-axis, you have the percent of air for your airflow measurement, and then on the y-axis is the capacity error. The orange line I just gave you as a reference of this would be if they're completely linear. And you can see that it is somewhat linear, but the slope is greater than 1. So any increase in error in your airflow measurement has a larger impact in the total capacity measurement. Yeah. Sorry, blue is the error. Orange is just the reference of the slope of 1. The capacity is the amount of heating or cooling that is essentially provided to the room. I mean, formally it's defined as the enthalpy change in the air, so you're talking about both temperature change and moisture change. But in this case, just to simplify it, I was only looking at the temperature change. Does that make sense? Perfect. On the market, there are obviously, this is a measurement that's taken numerous times, so there are various tools that are around. Two of the most common are hot wire anemometers and pitot tubes. So here, you see this is a pitot tube device. And for those that are not familiar with it, a pitot tube allows you to capture the dynamic and static pressure in a ducting system, which then you can use various relations to calculate the airflow rate based off of the velocity of the air. To take that type of airflow measurement, you would have to put the pitot tube itself inside the actual duct to get to the airflow, and then you would need a device that's capable of reading this differential pressure. The second option is a hot wire anemometer, which is basically a small electric circuit that you put in the airflow, and based off of a temperature measurement based on the current that is going through the circuit, you're able to tell how much air must be passing to remove that amount of heat. So to use these devices, you can't just put them directly in the duct, take one measurement, and call that good. That's not how fluid dynamics really works. So to account for non-laminar flow, there's a technique called log Chebyshev, where you have to divide your cross-sectional area of the duct, whatever the air is flowing through, into a grid, and then you take a measurement at each one of these points and then weight it accordingly, and then that would give you your bulk airflow. With a pitot tube, if you did have a case where you had a well-developed airflow, you could just put it in the center of the flow path, and then you could develop the relationship as well. However, ducting systems in the real world are not ever designed to have laminar flow. They're designed to get air from one place to another using as little material as possible. So they don't really care that you're able to take an accurate measurement. But as you can kind of already start to see, this is getting fairly complicated, and that these numbers themselves are fairly precise. So you could think like, okay, this isn't too bad. I just need to drill essentially 8 holes, or 4 holes in this case, and then based off of whatever device I put in there, I could have a relatively accurate measurement of how far it is in the duct. However, one thing that you start to lose is both of these devices have to be oriented in the direction of the flow. So that's another case where you can assume that a duct is running down a room, so at the point that you're measuring it, it is running parallel to the duct. But if you have a little bit of an eddy or any type of turbulence, you might not actually be in the correct flow path. So the precision, along with all the small errors that you could make with orienting the sensor incorrectly, or not being in the exact point, just continue to add to the inaccuracy of these techniques. I had mentioned in terms of leakage, I'll talk about this first and then do the leakage. Another option for measuring flow is called a flow hood. I'm not sure who isn't familiar with this, but does anyone need a further explanation of a flow hood? Cool. So a flow hood is basically a device that you just put over a register like this one in the room, and then it has like a calibrated fan or a pressure sensor array that is, so it captures all the air, pushes it through the sensor, and you are able to measure the flow rate. The pitfalls with these are, you're only capturing the air coming through one grill. So if you wanted to capture the total airflow rate of the whole system, you'd have to go to every single grill and then add those up. But one thing that commonly happens in large commercial systems is the air that's moving through the fan and the air that is moving through the ducts do not equal because you have leakage. However, if you were only looking at the ducts, you would never know if you had a giant hole upstream. You just know what's coming through that register at that time. Another pitfall is they have a really small useful range. It's because of how the actual application that they're used in, but you would have to buy multiple of them to be able to measure air in a range of airflows. This duct blaster system is a very common system in how you would measure leakage in your ducts. The way that it works is you would plug off all of your registers and use this system to pressurize it. And this system is a calibrated fan with various orifice plates. So based off of the differential pressure in that fan, it's able to calculate how much air is needed to maintain a certain pressure in the duct, and that correlates to give you what your actual leakage is. So this works pretty well and pretty quick, but the one pitfall with this is you're not measuring the leakage at the pressures that the system normally operates. You're adding pressure to the system. So the way that you get the pressure at normal operating conditions is by interpolation, which works fairly well, but there's obviously inherent issues when you start to run that regression from the higher pressures down to actual operating pressures. So I mentioned a couple of these already, so pitot tubes and anemometers, they're viable options, but as you try to take high quality measurements, the methods of practice start to break down. It's not always easy to be in actually get into a location where you could take one of those measurements, and then the flow hoods are limited by the fact that you're only getting the grill information. And this is just re-echoing what I just said about actually measuring at the system pressure that it normally operates as opposed to a raised or lower pressure. And then secondly, this system that I'm going to talk about a little bit more is we can actually measure where your ventilation airflow is going. All right, so what is the tracer gas airflow measurement system? Oh, yeah, that wrong button. All right, in the simplest case, we're looking for the changing concentration of a gas in the airstream that we're looking for. So in the most simplest case, if we could have something that is not present in air and we inject that into an airflow, then measuring the concentration difference from 0 gives us what that airflow rate is. If that's confusing, concentration is really just a fraction. It has no units. So it's just mass flow rate in, mass flow rate out with a fraction. The way that we do it is we use carbon dioxide as our tracer. We do that for a couple of reasons. One, it's already present in the air, so people are less concerned when you're telling them that you're injecting a gas into their airstream. Two, it's also much easier to purchase and it's cheap. However, it adds the additional complication that you now have to account for the background concentration before you started taking your measurement. So this is the fundamental equation of our system. It takes the mass flow rate that we inject into the air, looks at the difference in the concentration between before we injected and while we're injecting, and from that you get your airflow rate. So this is what a typical measurement would look like. So this, on the x-axis, this is time. On the far right side, this is, or left side, sorry. This would be the start of a test, and you can see down here, this is the signal from our CO2 injection, a nice steady injection. And then you see the corresponding rise from the baseline of 400 up to this pulse concentration of about 1500, along with this time delay. So this time delay is just the transient between where we injected and where we're sensing. So then you take this information and you analyze it with that equation to get your actual airflow. I realize now that this probably should have been earlier. So this is an overview. This is just a schematic of the system. And I've mentioned a couple terms, mainly the mass flow controller. So the way that we have is we have a CO2 tank. That CO2 tank has to get regulated down to work with the mass flow controller. And this mass flow controller is constantly measuring the parameters of the CO2 gas. So this is what's actually controlling our mass flow rate. And then we inject that into the duct stream. Once it's injected, and it's not pictured on here, we just use a simple gas analyzer to collect a sample of the air, measure the CO2 concentration, and that's how we get our 2 data points. So the big advantages of these is you can measure in the actual airstream. So what that does is that allows you to actually get the fan airflow without having to worry about the pressures or anything that the fan's operating at that could potentially damage your equipment. We can get ventilation airflow, and you could think of this in two different ways. One would be you could actually measure the flow that is coming through your ventilation air duct, but a second way would be just looking at the CO2 concentrations in the air. So just to give everyone a basis, outside is roughly 4 to 450 on average. In an office building that's well ventilated, you're more in the 600 to 700 range. And just to quickly jump back, our pulse is all the way up here at 1500. So even if you were in a heavily occupied office building, that's still enough of a signal change or concentration change that we can accurately measure what's going on. You can figure out mixing fractions based off of the CO2 concentrations, and again, the same thing with the air change range. You can flood a room with CO2 and then essentially see how long it takes to return to normal conditions. So, how do you use it? So the whole thing with the tracer gas system is you are essentially tagging a slug of air that is moving past a certain point. So wherever you're injecting, that is the airflow rate that you're measuring. So the injection and the concentration measurement are done in two separate locations. And it's easy to think, oh, well, where I'm measuring is where the actual flow rate is, and that's not the case. It's where you actually injected. And this has some pretty cool benefits because a lot of HVAC systems have ducting systems that branch, and they branch immediately after the fan. So if you tag that air before it goes through the fan, and then it goes through the distributed duct system, the measurement that you're capturing is the air that went through the fan, not what's actually going through each one of those individual ducts. So just to give you a visual example, so this is a RTU and an indirect evaporative cooler system that we were measuring a couple years ago. And we would inject just downstream of the fans of this system, and we would measure the concentration change as it went into the building, and that would give us the air that was moving between these 2 points. And the same thing for this is how we could tell how much ventilation is coming in, or what percentage of the air that a fan is moving is coming from outside. You can take a CO2 concentration measurement at various locations, and as long as you have the one, essentially you could have multiple streams, and as long as you are measuring where the streams come together, you can back out what fraction of each one of those streams is additive or contributes to the total. So our system has been developed over the last 6 to 7 years, but recently we got a grant from the UCOP to try and commercialize this product. The university itself holds the patent for the idea of using a tracer gas as an airflow measurement system. It's actually by LB&L in Berkeley. However, our addition to this is twofold. One is using a controlled injection plus a heating element. So we've appended onto that, or in the process of trying to append onto that patent. Through this effort, we were taking our device, which at the time we would just consider an engineering tool or a prototype. I mean, unless you had worked with it before, there was really no opportunity for you to figure out how to use it, and try to turn that into a product that anyone with an idea of what this airflow measurement should be could be able to take it off the shelf and use it. We developed a whipping-based injection system, and what that was about is as you're injecting CO2 into the airstream, you need something to mix that CO2 into the airstream. Because one fundamental assumption of all of this is that the tracer gas is well mixed into the airstream that you're measuring. And the problem that you run into is if you just did a single point injection, if you did a single point injection into a duct that had non-turbulent flow, the rate of mixing would be governed by the diffusion coefficient. And the diffusion coefficient versus, I'm going to say, a typical velocity of air through a duct, there's a 6 order of magnitude difference. So by the time that you were trying to measure your air, that gas is really not going to diffuse at all. So this whipping system is exactly what it sounds. We took our injection from essentially a linear array and turned it into 4 to 8 discrete points. And at the tips of those points are very flexible rubber tubing that, based off of excuse me, the pressure difference between the injection and the ambient air, whip around. So now CO2 is essentially being distributed stochastically throughout the entire cross-sectional area, which gives us better mixing and more accurate measurements. So our device is accurate. It's more accurate than pretty much anything on the market, but the bigger part of this is the range. So I had mentioned about those flow hoods. You can get fairly accurate. What I've seen is about 2.5%, but you're looking at a flow range of about 500 CFM. We can maintain this accuracy with our device between 20 CFM and 10,000 CFM, and that's 4 orders of magnitude. And that's just based off of the way that we sized everything. I mean, this was affected by the fact that we're the ones that use this tool, so we designed it to be in the range that we most commonly use, which is this, based off of this accuracy. The way that it's designed, you could use it modularly, or you could scale up components that you could take this accuracy range and move it to wherever you wanted. But in this device as well, if you could live with a little less accuracy, you could go all the way up to 30,000 CFM. We packaged it into a rugged design. Rooftops are dirty and you're climbing up and down ladders, so it needed to be protected. And then we did everything that we could to reduce the operational costs because some of the sensors that we use are fairly expensive. So now that I've talked about it, here it is. So our system is in 4 components. You have your CO2 tank. This larger Pelican case, which I'll show you more about in a second, is the injector. This is what holds the gas analyzer. And then here you can see the whipping tubing that we use along with power cords and everything else that it takes to run the system. As you open the Pelican case, you see you have pressure gauges and everything showing you the pressure of the gas coming in and leaving, the current output of the mass flow controller, a convenience outlet, and then wireless communications. For the gas analyzer, everything again is hidden. It's battery operated, which makes it very convenient because if you're on our rooftop and you have to measure below the roof, it's actually fairly hard to get a communications line through the roof without drilling a hole, and they don't like when you do that. So we designed this so that you could tuck it up into a T-bar ceiling, so you could measure across the roof if you needed to. Otherwise, you can run tubing to wherever you need to. It has 3 different measuring points. So you can take those outside air fractions that I was briefly talking about. Inside there's valves so that it can automatically switch between the 3. And yeah. I talked about internal workings. This just gives you an idea of how the tubing is actually run and everything to actually fit within that case. Matt and I recently had to take it apart, and we did not leave ourselves with a lot of room to really work, which is good because it keeps everything compact, but it's not necessarily the most field serviceable device out there. So you can see the gas will come in, it'll be heated up, it'll flow through the regulator, and then through the mass flow controller or bypass the system, which helps during depressurization at the end of a test. So we, as this product had been developed, we had done a lot of theoretical uncertainty analysis based off of the propagation of the various sensors through airflow and everything like that. But the last big part of this project was to actually validate it. And what we did is we validated it in our own lab. So in our environmental chamber, we have a very accurate nozzle box. So we essentially set our system up along with the nozzle box on the same airstream. And then we compared the performance. So what you can see here is our theoretical uncertainty. Each line is an injection rate. So this is you're injecting anywhere from 2.5 standard liters per minute to 500, which is the maximum of our controller at the moment. Notice that the airflow is on a log scale. so that you can go from 10 to 10,000. And then there is essentially three, well, in this one you only see two, surfaces that define the range at which we can operate in. We can't be any more accurate in this area. We can't get more accurate here. And then it goes back up over here. And you can see that across this 2%, we can flow between 20 and 10,000 and pick one of these injection rates and be less than 2% accurate in terms of our airflow. This chart is the same thing, except we're looking at actual plus or minus CFM instead of percent uncertainty. And then finally, this is zoomed out so that you can see this side of the chart, and that if you did want to go all the way up to 30,000 CFM, you would still be at about 4.5%. And if you wanted to live with a less accurate number, you could go even further with the same system. So here are the results at the three flow conditions that we tested. Orange is the result from the nozzle box, and you can see it's very accurate based off of how tight the error bars are. And the tracer gas system has a little more uncertainty, but everything is within uncertainty of each other. So the system works how we designed it to. So when I talk about this, I always enjoy sharing the stories of kind of how we got here in terms of engineering design, because it was a process, and lessons learned can be shared and help other people in terms of their design. So this original idea for this interpretation of a tracer gas system was actually originally a senior design project. They basically developed the technique. However, the device was so small that it couldn't really measure a very high airflow, and it required multiple computers to run and 150-foot USB cords to be able to put things where you wanted them to. We iterated on that to increase our capacity in terms of the amount of air that we could measure. So we were running with two mass flow controllers in parallel. Again, we still had the two computers, the really long USB cords, and then this is a big thing. We learned a very important lesson about things you need to know about what you're actually doing with your tracer. And what I mean by that is, so this is the phase diagram for carbon dioxide. You have absolute pressure and enthalpy. And this is just an example of what that 20-pound CO2 tank looks like. You have a amount of liquid CO2 and then gaseous CO2, and because this is a closed system at this point, you have a saturated liquid and a saturated vapor. So you're sitting within the dome. I know this is going to seem like a foreign concept in a second, but we'll get there. When the issue that we run into is when we regulate the pressure down, we end up going from a point of saturated vapor to the triple point, where you could have anything. You could have solid CO2, you could have gaseous CO2, you have everything. It's the triple point. This is where we needed to be to not damage our equipment. So what we learned is we really needed to heat the system to be able to operate it for a long period of time and stay within the happy range for all of the equipment that we were using. So from there, we iterated again. We added the wireless communications that I talked about and battery operation for the gas analyzer. We made it so that you could run the system with a single computer using LabVIEW. However, even though we had made these significant improvements, it still wasn't very user-friendly, partially because communicating to multiple serial devices via LabVIEW is not trivial. So the last big push of our project was to make it as friendly as possible. And at this point, the only thing that it pretty much can't do is calculate your airflow for you in real time, but there's no longer any communication issues or stability issues. And then this is just a picture of the previous generation of where we started. So that's really all I have. Any questions? So for a high airflow rate, you have to be able to raise the CO2 concentration in that airflow. So 30,000 CFM. So the 30,000 CFM number was used because that's typical for like a large commercial building air handler. And it's a part of the like air balancing industry that they struggle with because they have the situation where I was talking about, where they go around and measure all the grills, and then they'll use like a hot wire anemometer traverse or something to measure what's actually moving through the air handler, and those can be off by tens of thousands of CFM. So in this system, you could very quickly get that fan flow. Where it becomes more challenging is when you wanted to quantify each individual grill flow, which you could do, but it would just take longer because you have to move the injection to each one. Ben?
So you mentioned
Yeah. Yeah.
what is
So it would be time. So the whole thing, the business case for this would be man hours reduced. Part of the issue that we have run into is that we kind of have conflicting priorities, that us being more experiment-based and academic, we obviously want the really high accuracy, whereas the industry itself seems to be okay with far less accuracy. So there is some play that we could be there. But yeah, the big thing that this would do is save man hours, because instead of a job that may take 3 or 4 people a day to do the setup and takedown for this, maybe an hour, and then your measurement may only take an hour. So you could potentially cut half of the man hours needed to take a measurement. Yeah, I mean, so that's the easiest way for us to demonstrate it. But the other part of the business case is, I mean, a system like this is going to, even with all the research that we did to try and make it as cost effective as possible, is still on the order of about $7,000.
this system is $7,000,
Yeah, not including the computer.
but how much per job that it does?
Right. So I mean that becomes harder to quantify, and we didn't actually go that far into it because of the labor rates, where you are, what you're actually trying to do. So there's a large upfront cost with the idea that you would save a lot of labor, but we don't necessarily have the information to stand on the soapbox for those numbers and prove that it would save that labor. So they just see it as a high cost device. Should. It would be interesting to potentially take it to their facility in Fairfield and play around with it. But yeah, so I mean, at this point, it just kind of works as a research tool.
Well, no, I think if you have patents, right?
Yeah.
You get the idea is that
Yeah.
right, and it's maybe it's existing market, or
So there are 2 main companies, and the conversations that we've had with them is accuracy is not their driver, like upfront cost is. So
but if you're saving man hours,
yeah, so I mean, like selling to those, it seems more like we have to sell at the level of like the contracting company to be like, we can save you man hours if you use this tool, as opposed to trying to advertise this as a tool through the normal tool channels. Yeah, so one avenue that was talked about but we never got to pursue was actually doing stuff on campus with the Eco office, because in the few conversations that we've had with them and the facilities that work on the larger buildings, they're very interested with this for the idea of like getting the air handler level flow. And they're one of the people that, they're the group of people that directed us to thinking of how fewer hours this would take to actually take the measurement. So there's an opportunity there to try and collect some more information as well. Mhm. Yeah. Yeah. Yeah, we had never considered the rental subscription service model. But, yeah.
You didn't always, I'm in there and I often say, hey, they're doing stuff on dryers, improving that.
Yeah.
What is it? It was before measuring the temperature of the in versus the out, or the humidity of the in or out?
So what is, well, I won't go too far into it, but essentially the idea of an automatic termination control is relatively new to dryers. And more importantly, there hasn't been a way to actually test them until 2015. And even from the available data, the problem is there's two ways that you can certify your dryer to meet the federal minimum standard at this point. But when you look at that when you look at that information that they've passed, you don't know whether or not they passed because of the time dry cycle or the automatic drying cycle. So prior to 2015, it was just a gimmick that you could add, which I'm sure a lot of people were like, oh, this is awesome, I'll buy this. And the data showed that those systems used way more energy in that mode than just a time dry. And the way that those systems typically work is there's a moisture sensor inside the drum, or right at the front, like by the lint screen, and there's a temperature sensor in the exhaust. And from those two signals, that's how they determine that the clothes are dry. So in our thinking, there's issues with that because the fabric types that you dry are not uniform. So if you had, our great example is like if you have a bed sheet, or so say you're drying bedding and towels. If all of the bedding ends up in the front touching that moisture sensor, the dryer turns off and those towels are still sopping wet. So our idea is we look at the temperature of the air going into the dryer and leaving the dryer, and from that we're able to pretty accurately determine when the load is dry. But through that technique, what's unique about our idea is you're able to calculate what the mass of the dry clothes were and what the mass of the water added to the load was. Which we're hoping people might be interested in terms of like a real-time energy efficiency metric that may help you run your dryer more efficiently or know when something's wrong before you had like a dryer fire. Yeah. Yeah, there'll be another opportunity to hear about that one. But general, just rule of thumb, the more stuff in your dryer, the more efficient it works. Yeah. Yep. I mean, you're limited by your washing machine. But yeah, so much heat is added into that dryer that slowing the air down helps. So you don't really, dry more and it's more efficient. All right, I will hand it over to Curtis.
Hope you guys don't have a hard stop. All right, let me figure this thing out really quick. Okay, so Curtis Harrington, engineer at the Western Cooling Efficiency Center. I'm going to talk today about another patent that we've developed at WCEC, the aerosol sealing process, and this is a project looking at applying it to new construction single-family homes. So this presentation is going to go over some of the benefits of air sealing, the basic concept of aerosol envelope sealing, talk about the Building America project, which I'm going to present at ACEEE as well. and the path forward for the research. So really briefly on the benefits of air sealing your buildings. Heating and cooling is responsible for a large fraction of the overall energy use in buildings. It's 48% in residential and 35% in commercial. And infiltration is responsible for a large fraction of that. It's about 29% of the overall heating and cooling in the building. Now, granted, some of that's for ventilation purposes that you can't avoid, but you can use things such as HRVs or ERVs to try to, capture some of that energy that you're rejecting from your building and replace it. But there's also a lot of uncontrolled infiltration that we would just like to avoid in general to save on heating and cooling. And as we move forward and better insulate our homes and build better buildings, this fraction due to infiltration is just going to increase. So it's going to become even larger problem as we build better buildings. Envelope tightness standards are only recently becoming kind of standardized in codes. So coming up with cost-effective approaches for builders to be able to tighten their buildings is sought, and it would improve and simplify adherence to the code. Yeah. The fraction. In the fraction, the 29% would increase. Right. Assuming the building envelope absolute impact doesn't change and your building becomes more insulated, then it becomes a bigger fraction of the heating and cooling. Right. Yeah. Okay, so the basic concept of aerosol envelope sealing is you pressurize your building with standard blower door, similar to the duct blaster that Caton kind of mentioned earlier, while applying an aerosol fog to the space. As the air escapes through leaks in the building shell, the particles are transported to those leaks where they impact and stick. Because you're using a blower door to facilitate the sealing process, you're also able to track the leakage in real time, so you can stop the process when a particular target is met, or you can see when there's no more sealing happening, and you can stop then. Essentially, it finds and seals leaks missed by manual sealing methods. So you don't need to know where leaks are in a building. You just need to understand if there's like large holes that you need to address that the aerosol cannot seal. And so the general rule of thumb is this aerosol will seal about a 1/2 inch wide gap. And here's an illustration kind of further. Don't need to go into details, but you pressurize. There's leaks. Your sprayers are in there. Particles are transported to those leaks. It seals up, and the computer lets you know that it's all sealed. Okay, so for the Building America project, we've done a lot of demonstrations of this technology in the past. It's been generally really effective. So this project's looking at, okay, now we know it works. How do we apply this to standard construction practices? So we want to determine the most appropriate time to apply the process in a standard construction schedule, measure the performance of aerosol sealing relative to a baseline homes that were not sealed or were sealed with conventional methods, determine existing sealing efforts that could potentially be removed from standard building practices to save on labor costs for the builder. The goal of this is not just to get buildings really tight, it's also to have a cost-effective strategy moving forward. So determine cost-effectiveness of aerosol sealing is key. These are the project partners. Center for Energy and Environment is doing an identical study in Minnesota. Building Knowledge Incorporated and University of Minnesota's Cold Climate Housing Program are acting as consultants on the project. And Aerosol is providing the sealing under Aero Barrier is the name of the technology. And we're working with 2 builders in both California and Minnesota. Okay, so here's the basic project approach. We start by doing a house leakage assessment. We'll go walk around the building, look at how their conventional sealing methods are applied, do an aerosol demonstration if the builder's not aware of the process and wants to learn more, and then meet with the builder and go over potential options for how to apply this to their construction style. Come up with two potential options for when to apply it, and then perform sealing in both of those options in at least 2 homes each. And then evaluate the impact relative to baseline homes that were sealed with conventional methods. We'll then look at all the data and decide what the most promising approach seems to be, and refine that process potentially, and then apply the refined approach in 3 to 4 more homes. So this is a chart of the features in a building that need to be sealed. Generally, they're manually sealed, and this is the Energy Star Rater field checklist. I don't expect you to read this all, but essentially what we're showing here is all these cells in pink are places we think the aerosol could replace any manual sealing efforts. It's clearly a large majority of what needs to be sealed in a home, so there could be a lot of cost savings for builders if they were to use this process over some manual sealing techniques. All right, so moving on to some interim results. We've worked with one builder in California. These homes were designed with sealed attics, which is a fairly new kind of approach to building homes, although I think it might become more popular as we move forward with Title 24. This builder is using open cell spray foam at the roof deck and at the rim joist, and that basically seals and insulates the home in kind of one product. They use fiberglass and mineral wool in the wall cavity. The foam is not really cost effective for the builder, so wherever they can get away with fiberglass and mineral wool, they tend to try to do that. They have an HRV integrated into the air handler, which is important when you're sealing buildings. You need to make sure it's ventilated properly. So a balanced ventilation approach, such as an HRV, is a good way to do that. And this builder is already trying to build a high-performance home. They're trying to reach 800 CFM at 50 pascals of leakage, which is about 2 to 2.5 air changes per hour. For reference, the Title 24 requirement is about 5 air changes per hour in California. Other states have more aggressive standards, like in Minnesota it's 3 air changes per hour for the state, and then DOE and Energy Star have even more stringent standards than that. All right, here's some photos of conventional sealing for this first builder that we did an assessment of. So they used canned foam in between studs that are butted up against one another. They have a foam gasket and canned foam at the sill plate, and they use this gasket here to seal the drywall. Those are just some examples of what they use. So we came up with 2 options for this builder. The first option was to seal the home after open cell spray foam, which seems like the most obvious time to apply aerosols because the large gaps have been sealed by the foam. And then option 2, we wanted to see if we could seal the home before they do the open cell spray foam in order to see if we can potentially allow the builder to use a different insulation approach that's more cost effective. The issue there is that there has to be some pre-sealing of large holes and gaps before you do the aerosol. Both of these options are before drywall is installed in the home, and there's some advantages to that. When you seal before drywall, it addresses the outer wall surface, so infiltration from outside doesn't enter the wall cavity at all. Seals are less prone to damage in the wall cavity. Once the drywall's up, you can't really access those seals. And there's easier aerosol distribution, which is, I think, pretty key because setting up your spray nozzles can be kind of a challenge when there's drywall in place. You have to, in general, we try to put one in every room, but in homes there's like large closets and small bathrooms and things like that it's not certain how to apply the aerosol nozzle to those spaces. So when you have a big open kind of format, it's a lot easier to apply. Yeah, I'm not going to go into that. All right, so this is what the building looked like under option 1. You got the foam at the roof deck. That's up against the top of the roof, or on the bottom side of the roof. And then you have the rim joist all foamed up here. This fiberglass was in place. This wouldn't be there when we do the aerosol installation. It tends to filter out the particles. It was just the best picture I had of the rim joist. So the results for option 1. The buildings started out at about 3.5 to 4.5 air changes per hour. We sealed them down by 75%, in one case less than an hour, and the other one hour and a half or so. So we were really happy with that. We got it down to about an air change per hour. So we already got this building to well beyond what the builder was trying to reach with their goal, and so that was encouraging. Here are some example seals formed. Under each of these trusses, you see a seal was formed there, as well as at this corner of the wall assembly. Kind of complex geometry there. The foam did not address that. So those are some examples of places you might not expect to see or know that it's leaking there, and the aerosol finds it. You'll also notice it's a pretty clean seal. There's not a bunch of gray sealant sprayed all over the foam. It really just targets the leaks. All right, now option 2, you see the exposed roof deck. There's no foam in. There's all these penetrations in the rim joist, and essentially these have to be dealt with prior to aerosol sealing. So some pre-sealing work was necessary. The large penetrations needed to be sealed, so we tracked time and materials for our team to go out and seal these prior to the aero barrier with canned foam. We did this in 2 approaches. The first approach, we just sealed the obvious large gaps that we knew needed to be sealed. And then in the second approach, after doing that once, you'll see a leak like this and you have a can of foam and you're like, well, let me just seal that really quick since I'm here. So we spent a little more time if there was an obvious leak and we had the can of foam. We tried sealing that just to address it as quickly as possible. And this is my surprise monkey slide. I just don't have that monkey picture in here. So when you get to the building, in many cases I've come and it's not in the stage that I expect it to be in. Luckily there wasn't like fiberglass in the walls or something that would have been a killer, which happened to me last month. But there was this large gap here, and Daniel's hand shows how big that gap is. It's about 2 inches all the way around the eave of this home. So we expected to see this rigid foam to be installed at this point, where we could seal that gap with the aerosol. We could not seal this. So we tracked time and materials and did our best to seal those gaps with foam and rigid foam and canned foam. I separated the effort for each of these so that I don't expect to have to do this in normal practice, but I did track the time and materials. So in the first case, we spent less time, just dealt with the large gaps. It was only about 1.5 person hours and 3 cans of foam to address all of the leaks in the rim joist. The eaves was fairly easy, 1.5 person hours. So that's a 2-man team, less than an hour, and 4 cans of foam. Okay, so for the second one, we spent a little more time. We sealed things like this. There was a gap you could see around this plumbing. It took 4.5 person hours and 6 cans of foam. In that case, the eaves were essentially the same. It looks like we got a little faster the second time around, but not a lot. And I will note this is all work performed by inexperienced staff at the WCEC. I'm sure that a professional contractor could do this much better and faster. All right, option 2 results. So you'll notice one building's much leakier than the other. That's the one that we did not spend as much time manually sealing. They started out at 15 air changes per hour in one case and 9 in the other. And in this case, we sealed 85% or so of the leakage in the home, bringing it down to pretty much where the builder was trying to get to. So 2 to 1.5 air changes per hour at 50 pascals, which is really impressive. I don't really have a good slide to show this, but I think the manual sealing effort that we spent 4.5 hours doing, I don't think is really necessary. We got to 2 air changes per hour after an hour or 2.5 hours of injection, and the amount of time it would require to keep or to do the canned foam didn't seem really appropriate or necessary. The builder also came back and did the foam, so we measured the building after they foamed it, and these buildings got down to an air change, just kind of about where we got with the option 1 result. Here's some example seals formed at the rim joist at this external electrical outlet, and this is where 2 studs are butted up against one another. This red mark shows that the contractor was planning on using foam there. They wanted foam applied, but it's not necessary because the aerosol sealed it. And while it doesn't look like a complete seal, a lot of times these seals form deeper in the crack, so you can't necessarily see it. It doesn't always form on the leading edge. So even though it looks like it's not completely sealed, I assure you it was. All right, so here's the summary of results for both options. The dark blue bars are when we walked into the building, so before the aerosol sealing, and the light blue is after aerosol sealing. Obviously, option 1, the building was tighter. It had the open cell spray foam applied. We got the buildings down to about an air change, and then option 2 are much leakier. What I want to point out specifically with this is that these, after aerosol sealing, the building prior to foaming, so the yellow bars show after they foamed the building. We got the building tighter than the building was tighter than the foam was able to get to the building. So this is the leakage of the building with just foam applied, and this is the leakage of the building with just aerosols. So this demonstrates that the builder could have used a different insulation approach and met their leakage targets. Here's some baseline homes that we measured. So this is after they foamed the building, and then green is the end of construction. So on average, we got the buildings to about 1.1 air changes in both options versus 1.8 air changes per hour using standard approaches. 1.8 is pretty tight. They were meeting their target without using this process. So I think the key to this project is finding things that they did that they can potentially just not do and apply the aerosol instead and get better reliability because you're not relying on manual techniques, and you can just subcontract your air sealing out to an external company, and it I think would take some pressure off the builder. Okay, this is just another summary. Average was 1.1 air changes per hour, which is 39% tighter than the control homes. It's 55% tighter than the zero energy ready requirement that DOE has of 2.5 air changes per hour for this climate zone. And aerosol sealing was demonstrated to be more effective than the spray foam, which allows the builder to use other insulation approaches. So moving forward with California homes, we're going to test the same sealed attic scenario with blown insulation at the roof deck, so instead of the spray foam, and we'll be able to do a good cost comparison of those techniques. That's planned for later this month. And develop strategies for ventilated attics. So I think in general, the majority of builders are still building buildings with ventilated attics. The approach is going to probably be very different for those cases. It'll probably have to be after drywall, is what it seems like. So we're looking forward to working with builders on that moving forward. All right, so on to the Minnesota results. The guys in Minnesota worked with one builder. The homes were designed with ventilated attics. They used closed-cell spray foam at the rim joist to deal with large penetrations through the house. They use an interior poly wrap, which is unique to that climate. It's a very cold climate, so the poly wrap acts as an air barrier as well as a moisture barrier. And they use fiberglass mineral wool similarly, and in the wall cavities, and then an ERV integrated into the central air handler. So similar conventional sealing techniques. They use caulking instead of foam, but essentially it's the same at the sill plate and between studs. Wire penetrations, they use canned foam. So a lot of similarities there. Okay, so the two options they came up with for this builder was to seal the home after spray foam, put a reinforced poly between the attic and at the ceiling of the top floor, between the attic and the building, which is where the air barrier would be, and maintain all other conventional sealing. Option 2, which they didn't agree to ultimately, because they weren't really comfortable with removing some of these things, was the same as option 1, although we suggested they don't use airtight electrical boxes. It may seem kind of minor, but these are a few dollars each more expensive than standard electrical boxes, and there's like 50 of them in this home. So there's some cost savings there. There's also interior poly, so besides the poly they put at the ceiling attic interface, they also wrap the entire inside with poly. You could instead use low permeability paint to deal with the moisture transfer, but the air barrier could be addressed with the aerosols. Here's the plots of the 4 demonstrations that they performed there. The red and the blue are kind of typical sealing profiles you'd expect to see. 2 hours of injection, sealing 80% is pretty typical. You'll notice the green and red stand out. They didn't have quite the sealing rate we'd expect, and they took a really long time. They were pushing 2.5 hours here. Or wait, that's even longer. Green and purple, sorry. The long ones. Yeah, so is that 4 hours of injection? Yeah, it's 4 hours of injection. There's also this blip here. The reinforced poly had given way in the middle of the aerosol sealing because you're trying to hold back this pressure of 100 pascals. And so they discovered that, and I think tape did dealt with it, and it came back down a little bit. But essentially what was happening here was the builder was ahead of schedule. Again, they came and the building wasn't quite in the same stage they expected, and there was fiberglass bats in the walls at this point. And so they were trying to like move it away from electrical outlets, and it didn't work very well. So key is don't install fiberglass before you do the aerosol. There's the failure of the poly at the ceiling. Aerosol tried to seal it, as you can see here. It maybe sealed that pretty well, but it wasn't gonna do the job. So here's some example seals. This is an aerosol seal. It looks like someone came through with a caulking gun and addressed that. There's all these seals at the wiring penetrations, electrical outlets, plumbing, all sealed up really well. These are kind of the overall results summary for that builder. This is a different builder altogether. We don't need to really talk about that. It was a different stage of construction. It was after drywall was installed. But these five, I should say, were all, this demo wasn't on the plot, but there was a really good result there. So in general, on the ones that didn't have bat insulation in the walls, we saw a really good sealing result, 70 to 85% sealed, and the average was 0.88 air changes per hour at 50 pascals. So really, really tight and better than the control homes. So again, briefly, the average was under an air change per hour. It was 41% tighter than the control homes. This was 56% tighter than the zero energy ready requirement of 2. So they have a little bit tighter requirement in that climate zone. We also found that the average tightness was 1 air change per hour at 50 pascals after sealing and before drywall. So it demonstrates you can remove all these features or sealing approaches after drywall or at the stage of drywall, so such as the poly sheet on the wall and the airtight electrical boxes are not required. So after demonstrating this to the builder, even though they didn't eliminate it for this demonstration, we still have another stage to go with this builder, and I think they're amenable to trying it without the poly wrap. Kind of hot off the press result is the latest houses they sealed. We're getting down to 0.6, which is the passive house requirement. It's about as tight as houses can get, really, and so they're getting even better as they go along. So next steps for Minnesota builder is to finish work with the first builder, potentially eliminate poly, and begin work with the second builder. All right, this is my last slide. This is basically where we think the research path is going forward. There's some work needed in commercial buildings. We just completed a project for the Department of Defense looking at non-residential retrofits and came across some interesting kind of results and challenges, particularly at the roof-to-wall connection. There's some weird architecture in buildings, and that proved to be a difficult spot to deal with. In some cases, there were very large gaps that required supplemental manual sealing for the aerosol to work, and in other cases, it didn't need any. So it's really a case-by-case basis, and understanding those buildings better and how aerosols could be applied to them would be a good thing moving forward. I'm interested in trying to apply it from the outside going in, but that's kind of a high-risk, high-reward type scenario research that maybe the feds would be willing to do at this point. So also application in existing homes. There's a huge opportunity in existing homes. Obviously, there's a lot more of them. They're much leakier. They have less efficient heating and cooling equipment. So being able to apply this to existing homes is huge, and that's really, we have a proposal we're writing right now to do this with the next round of Building America. We think the best time to do it is at time of tenant change, when things are removed from the space. It's not obvious that the aerosol will work very well with all your couches and knickknacks in there. And to avoid that kind of liability, I think it's best to remove it. So maybe at carpet replacement or flooring replacement, you could apply it. So we're going to look into that moving forward. And that's all I got.